Hi everyone, I'm Kerry Witkov. This is the first of a series of videos on how to do an experiment and analyze it. While these videos emphasize experimental data analysis informs an experimenter how best to do an experiment. When an experiment is repeated multiple times, different measured values are expected due to random factors that influence experimental results. For example, equipment vibration, electrical noise, temperature fluctuations. You get the picture. Every measurement has a statistical uncertainty associated with it. The plot on the left displays results of repeated measurements and a model line showing the expected result. Another possible experimental finding might be measured values that differ systematically in one direction from the expected results. That is, we obtain a discrepancy, as in the plot on the right, where results are systematically below a model line. Experimenters jump for joy when there's a discrepancy with an expected result, because it may signal the need for a new and better model, or even the discovery of a new effect, though more often than not, discrepancies are the result of systematic uncertainties due to experimental design or equipment. For example, using a meter stick that by repeated use has one end that is worn down introduces systematic uncertainties when measurements are taken from that end. About terminology, you may come across, especially in older literature, the phrase random errors. However, as these aren't errors in the strict sense of experimental mistakes, the best practice nowadays is to refer to measurement uncertainties as statistical uncertainties, not random errors. Similarly, the practice of referring to discrepancies as systematic error has been replaced by the phrase systematic uncertainties, as these may not be errors, they might even be new discoveries, though often not. Experimenters attempt to understand systematic uncertainties to eliminate them by improving the experiment or revising a model, while statistical uncertainty is something experimenters try to reduce but live with. This video is a first step towards working with statistical uncertainties. Later videos will round out our statistical toolkit. It's helpful to distinguish between precision and accuracy. Precision is how close measurements are to each other, while accuracy is how close measurements are to an expected result. To collect some data, let's use a simple reaction time experiment. You hold a meter stick vertically in front of you while a friend holds their open hand near a mark on the meter stick. Then you drop it and they catch it as quickly as they can. Your friend's reaction time can be estimated from this experiment using the kinematic relation between displacement, time, and acceleration for constant acceleration and no initial velocity. When taking the square root to solve for t, we'll reject the negative time solution as not being physically realizable. This isn't Star Trek. Here's a table of results of our first 5 trials. How should our friend estimate their average reaction time? One possibility is to simply average the displacements and substitute into the reaction time equation, obtaining the results shown. But a second possibility is to create a second column with a reaction time for each displacement, then average the reaction times to get one average reaction time. Now, notice the results are different. So this isn't merely an academic question to ask whether we should average the displacements or average the separate reaction times to obtain the average reaction time. Think about it for a moment. You might want to pause the video to ponder this or discuss it with others. Perhaps we should recall why we average data in the first place. Averaging causes deviations from a true value to cancel when deviations contribute equally and each has an equal chance of being positive or negative. Now, the reaction time equation applies a square root to the displacements. The square root weights some displacements more than others, so positive and negative deviations from a true value are weighted differently and can no longer be expected to cancel by simple averaging. Hence, the correct procedure is to average the displacements and substitute this one best displacement estimate into the reaction time equation. This is a rare example where the simpler of two algorithms is the right one to use. We can state this result in the form of a maxim to be remembered. Average the data, not the calculations. Did you note that the raw data, displacement, and the calculated reaction time were reported to 2 digits of precision, implying that measurements were taken to the nearest centimeter? Now, while meter sticks can measure down to millimeters, 3 digits of precision, and a 4th digit might even be estimated because the resolution of the human eye is about 1/10 of a millimeter, this experiment doesn't lend itself to high precision. The fingers grabbing the meter stick, they spread over several millimeters. So perhaps the experimenter was only sure about the nearest centimeter. This raises an important point. Since the data is no more precise than 2 digits of precision, any calculation based on this data, for example, the average reaction time, cannot exceed this precision. The precision of a calculation cannot exceed the precision of the least precise number that went into the calculation. While calculators and software can easily display many more digits, please resist the temptation to display them, as any digits beyond those justified by the least precise value that went into a calculation is false precision and actually reduces the credibility of a calculated result. This is so important. Let's write it down as the second maxim in this video. The result of a calculation can be no more precise than the precision of the least precise number that went into the calculation. Now that we have an average reaction time, it's time for our friend to publish their results. They submit their average reaction time to a journal, but the editor kicks it back with the comment, "You forgot something." What did our friend forget to submit? Average values provide no information about the variability of individual measurements that make up the average. In other words, the average reaction time submitted didn't include a measure of its statistical uncertainty. There's clearly a difference between the results of the following 2 data sets. Both data sets average to 0.23 seconds, but the data set on the left shows no variability, which is unusual and suspect, unlike the data set on the right. An average doesn't tell us the data set it was calculated from. Here's the original data. How can we measure its variability to have an estimate of statistical uncertainty? Well, listing all the data, that's usually difficult to read and impractical for large data sets. So the option to show all the data we can rule out. Giving the highs and lows, that is, the range, is better than nothing, but not by much, as it disregards all the other data and only characterizes outliers. So we'll rule that out. Taking the deviations, that is, the differences between each value from the mean, runs into a problem. And that problem is that the mean deviation will be 0. Why is that? The mean deviation must be 0 because deviations themselves are deviations from the mean and are equally likely to be above or below the mean and hence cancel. To get around the problem of 0 mean deviations, we have a few options. We could take the absolute value of the deviations before finding their mean. That would give positive values, but it's unwieldy working with absolute values in equations, and definitely not fun working with absolute values in calculus. A second option is to square the deviations. This solves one problem and creates another. The mean square deviation becomes positive, that's good, but we now have square units, square meters in this case. However, we can correct this by taking the square root. So there we have it, an algorithm for measuring data variability. So the algorithm is calculate the deviations, square them, find their mean, and take the square root. If you read this algorithm backwards, from right to left, you have the root mean square deviation, or RMS deviation. In fact, you can recreate the algorithm by reading root mean square deviation word by word from right to left as follows. First, write the deviations, square them, take their mean, and take the square root. Now, the rest of the world calls the root mean square deviation the standard deviation. Here's a visual look of the algorithm implemented step by step in Excel without using Excel's built-in function for standard deviation. Starting with the displacements and finding their mean, we take the deviations of each displacement from the mean, then we square the deviations, take the mean square deviations, and take their square root. Before submitting this statistical uncertainty to the journal, we recognize that the standard deviation of the displacements we found, 0.14 meters, isn't the statistical uncertainty of the average reaction time. It's a displacement, not a time. We need the uncertainty in time due to the uncertainty in displacement. And we can't just plug uncertainties into our kinematic equation because the equation has a square root. That is, it's nonlinear, and it would weight some uncertainties more than others. Remember, we faced the same issue when we recognized that we have to average the data and not the calculations. There is a method to go from the uncertainty in one variable to uncertainty in another when we have an equation that relates the variables. In the literature, this method is called error propagation, although of course uncertainty propagation would be a better name. To make it plausible, we start with what looks like the equation for a line with slope but no intercept. dy equals mdx, where the slope is dy dx. Substitute uncertainties for differentials as they're both small. You might be used to using sigma for standard deviation, and we'll do that here, but Don't get too comfortable with that notation, as we'll see before long. Take the derivative with respect to displacement in the reaction time kinematic equation and simplify. And we now get an expression for the uncertainty in time due to the uncertainty in displacement. We substitute the values we previously obtained, and we get an uncertainty in reaction time due to an uncertainty in displacement. So our friend proudly submits their average reaction time, 0.23 seconds, plus or minus 0.07 seconds. The journal editor receives the submission, and the manuscript is returned again with the comment, "There's still an error." What mistake did our friend make? Let's review everything our friend did right. They averaged the data, not the calculations, and presented the average reaction time. Good. They calculated the standard deviation of the displacements and transformed these to the standard deviation of the time measurement. Good. They submitted the standard deviation of reaction time as the uncertainty in the average reaction time. Oops, that's the problem. The uncertainty we submitted isn't the uncertainty in the average reaction time, it's the uncertainty of the individual measurements of reaction time. Now, individual reaction times have intrinsic variability due to biological factors. Perhaps random experimental factors also introduce additional sources of variability. For example, differences in how far our friend holds their fingers from the meter stick with each trial. The reaction time standard deviation we calculated is the intrinsic uncertainty associated with individual measurements due to factors largely outside our control. But we didn't submit individual reaction times. We submitted a mean reaction time, an average. Hence, we need the uncertainty of the mean, that is, the standard deviation of the mean reaction time, not the uncertainty of an individual reaction time. Now, how does the standard deviation of a mean value differ from a standard deviation of an individual value that makes up the mean? That's fairly easy to reason out. If we take more measurements, our estimate of the standard deviation associated with individual measurements may fluctuate a little, but won't change much because there's an intrinsic variability and we get a pretty good estimate of it even with relatively few trials. But what happens to our estimate of the uncertainty of a mean value when we increase the number of trials? The more trials, we should become more certain, that is, less uncertain, in our estimate of the mean. The standard deviation of a mean value should decrease with n, the number of trials. More trials should mean less uncertainty. Therefore, we expect the standard deviation of the mean should depend on two things. First, the standard deviation itself, because there's an intrinsic variability that we can't alter. Second, the number of trials, which we can alter. The standard deviation of the mean is called the standard error and is equal to the standard deviation divided by the square root of n. This can be derived based on summing random vectors as uncertainties add vectorially. The significance of standard error is it's an uncertainty that's in the control of the experimenter. If you want less uncertainty in an estimate of the mean, collect more data. Though note that the uncertainty improves only as the square root of n, so collecting 100 times more data only reduces the standard error 10 times. While much of the world uses the Greek letter sigma to denote standard deviation, in physics we reserve use of sigma for standard error, not standard deviation. The reason is simple. We should always do repeated measurements to obtain mean values. Mean values, first, allow cancellation of statistical uncertainty, and second, they allow use of the standard error, which puts statistical uncertainty in the hands of the experimenter. We'll no longer use sigma for standard deviation, which we'll now designate simply as SD. Sigma will designate standard error. In the next video, we'll discover yet a third reason to use mean values of our data. The standard error is calculated as the standard deviation divided by the square root of n, and our friend resubmits the manuscript for the third time. Success. The manuscript is accepted. Here's a half dozen takeaways from this video. First, average the data, not the calculations. That is, average before any transformations on the data take place. Two, a calculated value can be no more precise than the precision of the least precise value that went into the calculation. Three, standard deviation is the root mean square deviation, or RMS deviation, or RMSD. Standard error is the standard deviation of the mean and is denoted by sigma. Fifth, standard error equals the standard deviation divided by the square root of n. So it depends on the uncertainty or intrinsic variability in the phenomenon we're investigating, as well as the number of trials, which the latter is in the control of the experimenter. And six, there are many reasons to use mean values. Mean values reduce statistical uncertainty, and they allow the use of standard error, which can be reduced by the experimenter by taking more trials. Thank you for watching.